So welcome to our systems engineering course, and this is a presentation for chapter 6, which has to do with system tests, evaluation, and validation. Now normally, this is a very important topic, and normally it gets sort of relegated towards the end, so we're guilty on that here too. But I want to make sure that everybody understands that that does not minimize the importance of this topic. As a matter of fact, you end up spending on tests, evaluation, and validation anywhere from 2 to 6 times more time than what you invest in the actual design of the product. So normally 2 to 3 times as much time is average, is normal. And the reason for that is that test is not only an activity that you do while you are developing, but also it's an ongoing activity that you also do while the product is deployed in the field as a way of monitoring the ongoing quality and reliability of the product, as well as finding ways for continuous improvement in the processes that are used to manufacture the product. So I don't want you to get the idea that it is not important. It's actually very, very important. And the simple pragmatic reason that we spend so much time in the actual studying the actual development and design of the product is pragmatic in nature, because you do have to have something designed in order to test it. So that is first and foremost something that you have to do. But again, the quality of system and the mechanisms of feedback in a timely manner are very important, so the product development goes smoothly. So the things that we're going to cover in this chapter are the following. We're going to be talking about how do we determine the requirements for the system test, evaluation, and validation. And we also are going to be describing the different categories of system tests. How do we plan for it, how we prepare for it, how we think about all the things that we need so these activities go smoothly, as well as actually conducting the test and collecting data. We're going to talk about a little bit about the different reports. And then we're going to end the chapter giving you an example of a corrective action loop if there are system modifications that are required as an outcome of the different tests. So to start, we're going to kind of go back and look at the whole flow that we have been discussing in this course, starting with the definition of need and getting good requirements, then actually doing the development of the system, and then the evaluation. So we're actually going to talk about the differences between test and evaluation and validation, but at a high level. At some point where you are in the middle of the development and you're doing some type of evaluation or test, of course you're going to look at the results, and if they're satisfactory you can go on to the next step. But if they're not, you have to assess that, analyze those results, and come up with alternatives given external factors and constraints. So if there are no feasible alternatives, well, that's a big problem that could actually tie into the business plan for the project or the product. But if there are alternatives, then of course you implement the change, and again that's the kind of the loop that we're going to see at the end, and go back. And sometimes you don't have to go all the way back to the requirements. You can go back to the actual definition of the test. It could be a number of points that you can tie into for feedback. But again, this is a high level idea of how that goes. Now, the idea is that the concepts and the methods and the disciplines that we have discussed in this course, the idea is that they minimize that you go this way, that the test results are not satisfactory. But it can happen, and then the disciplines and concepts that we have discussed in this course minimize the likelihood that you end up in this area of not feasible alternatives. So because by that time you have looked at some other alternatives, and maybe you didn't choose them at that time, but now it's time to review those and revisit them, and maybe one of those alternatives are the ones that you implement next. If the one that you pick to begin with doesn't give you the satisfactory test results. So the whole idea is to apply all these techniques that we have learned in this course, so you don't end up with a dead project, essentially. In COSI has a dichotomy and terminology for defining different types of testing. We have discussed during the conceptual and some part of the preliminary design. We can see here a high depiction of the life cycle that we always go by. And we have discussed the analytical type of testing. So based on CAD, based on simulation and analytical models. So we're not going to rehash that. We discussed this already. The type 1 testing is the one that you do early on during the preliminary system design and some of the detailed design and development of the product. And those are based on some further and more sophisticated models, but also will be breadboards, mock-ups, rapid prototyping parts. So I am sure that even if you have not looked at them from that perspective, everything that you have learned in all the labs up to this point put you in a good place, in a good position to understand this type 1 testing, because that's essentially what you have been doing. Okay, so that one I'm not going to emphasize so much. Okay, the one that I'm going to go a little bit deeper on is this type 2, which actually is applied during the latter part of the design and development stage and the early part of the production, when we are doing what is called ramping to production. And that is just here at the beginning, but that's such a critical phase of the design, to go from a few prototypes that you may have at the end of the design and development to go to this part when you actually have ramped to production and are fully engaged on producing the volumes that you need to make your product successful from a market perspective and deploy it. That is a critical phase. That is a critical part, and is a lot of the products. That's sort of the weakest link. It's very hard to go from a few to thousands, and there are very few people that know how to do that correctly and efficiently from a cost perspective. So for that, you need this type 2 testing. You need this type 2 testing to be successful, and we're going to be talking in detail what that entails, what that is. Then type 3 refers to sort of the more general, more conventional type of test that you do during production. And type 4 refers to the types of tests that are done and ongoing as a way of sample the ongoing quality, reliability, and get data for continuous improvement of the product as well as the processes used to manufacture the product. So those are more straightforward. They actually evolved from the type 2 testing. So I'm going to really emphasize this type 2 testing here. Okay. And of course, all these types are widely elaborated in the textbook. You should be reading chapter 6. So let's look at what type 2 testing entails. So these are performance tests. So now that you start getting more, as you ramp to production, you start getting more quantities manufactured. You have a larger statistical sample to look at performance tests and the distribution of the accuracy and precision of those performance, technical performance metrics that we discussed back on the earlier chapter. You can do environmental qualification. So what are these types of environmental qualification? Drop tests. So remember, you have a product that's going to be shipped. It's going to be staged. So what is the resilience of the product to being dropped? So those are important concerns. Temperature variation. So there are tests such as temperature shock, where you actually change the temperature very quickly, and you see the reaction of the test of the product to these types of tests. You can do shake tests, where you actually subject the product to sudden accelerations, to vibration. You can subject the product to humidity, intense humidity and pressure conditions. So a lot of these tests are destructive in nature, because they actually stress the product beyond what you designed it for, but they also have the capability of accelerating the life of the product. So by exposing the product to these stressful conditions, you actually can see if the product is going to last, for example, 10 years. And there are many reliability models based on the materials that products are made of. The ones that I'm most familiar with is, of course, silicon, with my semiconductor background. But there is a way to, for example, if you increase the voltage and the temperature of semiconductors, you actually can simulate the aging of the oxides, and that will give you a measure about temp shock type testing, where you can subject products to sudden temperature changes, as well as subjecting products to sudden accelerations or vibration testing. They also intense humidity or pressure conditions. And what I was saying is that a lot of these types of testing are destructive in nature, because they are stressing the product beyond the environment that they were designed to operate in. But they have, there are many models based on materials, reliability models for different materials, of how you can actually accelerate the life of materials. And most of my familiarity is with semiconductor products, and in that case, we know that stressing semiconductor products with higher voltages and temperature stresses things like the oxides, and that can actually accelerate the life and tell you if a product is going to last 3, 5, or 7 years. Of course, you don't want to wait 7 years to just measure it empirically, but there are models that say if you overstress with this much voltage and you raise the temperature this much, that's a life acceleration factor of this much. So you can actually accelerate life, but by doing that, you're actually damaging the product to a point, because you have to look at when does it fail under those overstress conditions. So there are many tests like this, but these are the tests that you do when you're ramping to production, because that's when you start having a larger statistical sample of what you are producing. You don't have that type of statistical significance when you just have a few prototypes. So I did also, all this is here: environmental, structural tests, reliability, qualification. They're sort of in my mind, they're bunched up together. Also, I mentioned drop test. So you want to know if this product is packaged as is intended to be shipped, and the UPS guy drops it from the truck. Is it going to break, or is it well protected? So all these tests you do as you ramp to production. Also, the maintainability. You can start getting a statistical sample and statistically significant view of how easy the product can be maintained and can be supported. You can start deploying the product to a few users and personnel to start doing more tests and evaluation and collecting really significant amounts of data on the verification. On the software side, also, you can deploy software to users in an alpha or beta type of engagement to really get more data on software verification beyond the regular verification and debugging that is done during the coding. So this type 2 testing is very, very important as you transition from your development and a few prototypes to actually ramping to production, where is really where the promise of the project is going to materialize as you deploy it into the market. So how do we plan for a successful system test and evaluation? The most important thing, just like we did when we were planning for the product, and we tried to gather holistically and completely all the product requirements, is to identify all the tests that need to be accomplished. And so there is no substitute for good planning, and I think that we have that being a continuous theme throughout the course. So an identification of all the tests to be accomplished, and also who's responsible for doing that. So these are the sort of the 3 W's, who's going to do what, who's going to do, and where is it going to happen. So test location is also important. A clear description of the preparation for the test and what is the steps, the standard operating procedures for the test. That's important. So a lot of documentation becomes very important. So that basically gets put in a plan, okay? And also you may want to describe what type of test reporting you are expecting. So how do you consolidate the outcomes of the testing, and what is it that you want documented so that it is actionable? It is actionable not just to have it, but to help you in case that you have to do something about the results to mitigate some issue that may have come up. So this is this is an example. Again, it's a generic example of some fictitious type of equipment or design, where you have different types of components or parts of the system. Let's say that you have a system that has a subsystem that is totally new, and that is going to be integrated in some existing system. So you're not doing the whole system, but just a part of it that you are doing. You have already most of the system. Also, in this system, there is going to be, you're developing this from scratch, but also you are bringing in an off-the-shelf component that is already tested and verified and guaranteed by the vendor. Also, because by virtue of putting this new part, this new subsystem in the system, the software is new. You have to revamp the software in this fictitious example. And also you're going to need to test the system in a different manner, so it's going to have a new test equipment that you're going to be utilizing. Okay? And of course, you know that that's going to go into some operational facility. So what this example shows against the different types of testing is how these different types contrast to these different parts of the system, and how it contrasts with different types of tests. So type 1 test, the one that you have to do when you develop things and have early prototypes, that would be applicable to this new subsystem and also to the new software, because you're doing that from scratch. Okay? Then you're going to do type 2 testing. Somebody's here. That person. So you're also going to have to do type 2 testing that we just discussed on this new part. But also, as you bring this subsystem into the existing system, you're also going to have to do this type 2 testing in the overall system, as well as in the new test equipment that you're going to require. Okay? Then you're going to integrate everything, and type 3 testing refers to the same type of type 2 testing, but not with the same granularity, not with the same level of detail, because you already did the parts, or some of the parts, but here you're doing it on the whole thing. And then you deploy the system to the operational facility, and you do this ongoing operational facility-based type 4 testing, which again is a subset of type 2 and type 3, but not at the same level of detail. And also, as you integrate the system and you test it and validate it in the operational side, you have a mechanism of feedback to all the system design activities. So that is just a way of looking at a specific example, or albeit fictitious, but at a specific example, and how they align with the different types of testing. So now let's talk about this whole system test and evaluation. So this would be the type 3. Okay. Again, this is going to vary widely by system. What I want you to take away is the general spirit of the activities. So the key is for you to take this and adapt it to your specific project, to your specific product. But the spirit is what I want you to take away from this. So again, selection of test items and what are the procedures, the site. So a lot of the same things you can see: the personnel, the facilities and resources, what type of equipment do you need, how do you support these tests. You may need spare parts, repair parts, because you may be testing the maintainability and repairability of the system. What type of, this type of test 3 also, as you are beginning to deploy the system and the product into the operational side and the market, also start testing some of the supply chain issues and logistics of making the product successful as a business. So facilities and warehousing requirements, and what are the personal requirements, ongoing technical data requirements. So all that needs to be documented. So you can see that, it starts getting a little bit less technical, but now it starts tying even into supply chain issues and logistic issues as you start deploying getting out of the manufacturing mode and getting into the deployment of the system to the marketplace. So what is it that, when you ask this question, what should be testing? Well, what should we be testing? These are a few questions to keep in front of you. At any time, what you want to know is this: what is the true performance and the effectiveness of the system? We defined these things even back in chapter 3, okay? And as you get more product manufactured and you get a larger sample size and more statistical significance, you can start to see what is the true performance and the effectiveness of the system, but also the logistics. Things like the logistics and maintenance support infrastructure. So really, you start getting an omni view of everything that is going to take to make that product successful. You can get a lot of statistical data and look at distributions and a statistical analysis and metrics of the technical performance measures of the system. Are they really being met? What type of accuracy and precision distributions that you have? What type of control on those distributions your manufacturing processes are yielding? So these are you cannot get this from the initial development and design stage. You have to have enough what we call pilot runs, where we build anywhere from just a few hundreds, so a few hundreds of a product, and that's enough to get some meaningful statistical data on things like TPM distributions and things like that. So for these questions to be answered in a successful manner, you really need to go back to the requirements and how they stack up against the application of those requirements and the applicability of those requirements to the system. And hopefully, by doing all the things that we discussed in chapters 3 through 5, you did design, develop, and implement the capabilities that are responsive to those requirements. So, but now, not just on a handful of product, but on hundreds of them, that is really statistically significant, you can see if you really did do this, okay? And again, hopefully, if you have followed those methodologies and disciplines, you did do it, and your product will be successful. Now, in the book, there are, so sometimes I bring in this busy slides, and my intention is not to read it to you, but because this is in the book, and you can read it as well as I can, but it's really to highlight the importance that you should be reading the chapter, but things that I show like this, you should actually be studying. And there is a difference between reading and studying. So on this, you should pause, read it a couple of times, but think about it. Really try to bring it into some meaningful context of something that you are doing, that you're thinking about doing. And that's why I try to link this course so much to your upcoming senior projects. So try to think about these things in the context of something that you are passionate about, like your senior project, and that you are almost ready to start. So go through this list of the different types of test items and issues, and spend some time studying this. It is very important. It's kind of a good summary of everything that we're talking about in this chapter. So I have that in three slides here. This is pretty comprehensive. I'm going to wrap up the chapter. I just want to show, and this is a pretty short chapter. I just want to show an example of system evaluation corrective action loop. And again, this is something that you should put together for your own project in the context of your organization. Whether it's a huge organization, it may be much more complex than this. But if it's you and another team member doing a senior project, it may not be so busy. But still, the point is that you should have something. You should have some type of policy, some type of approach. So it's not ad hoc. So there is some discipline in what you're doing. So in this example, what we have is here starting with field operations. So the system is being deployed and is operating, and you have both test activities and also the actual operation of the system. I mean, many systems right now, with the ease of connectivity, a lot of the systems are continuously storing and feeding back metrics of their operation that can help in this data collection that can be done through the network. So you're going to be collecting data, and so you must have an infrastructure for storing that data. So this is essentially here, these two boxes comprise a database of not only the raw data, but also of some reports and results that come later. But from that raw data, you can do data analysis. So you have to define what that analysis is going to be, and that's going to be dependent on the data that you are collecting. Remember, this is a genetic approach here. You may be bringing some analytical models and contrasting that with actual data and making the model better, but at the same time using the outcomes of the model to understand the data that you're collecting from the field in a better way. So one recent technology that is taking a strong foothold is the concept of a digital twin. So that is where you have an actual digital model of the system, and you do simulations to proactively look at operational situations of the system in a less expensive manner, because this is simulation based, and you can contrast that with actual data. And you can also use these simulations to instruct the system on how to adaptively change itself and evolve to different operational conditions. So that's a very interesting technique and technology that is being used more and more these days in complex systems. So you do the data analysis, and if there is a problem, you look at any history on that problem. So that's why having these databases is important. And if there is a history and there was a corrective action, then you basically can reevaluate that corrective action. And there is not, then you have to evaluate that problem and see if the corrective action is required. Okay? If there is, again, you plan that corrective action, you develop a plan, materials, any type of data for system modification, and you go on to incorporating that into the system. And that goes back to the database, so it can be used later on. If another problem similar to that emerges, you can then find it from a history perspective. Okay? So again, this is a very general sort of example of a corrective action loop. but hopefully it gives you the idea of the main things: data collection, having a history of the problems, relying on that history so you don't have to reinvent and treat that problem as a new problem every time. But if it's new, going through a disciplined process of coming up with a corrective action and planning the incorporation of that change. So with that, this is the end of the chapter. So I thank you very much.